Hello! So, in this video, we're going to talk about the other types of stability which we can have. We can have 6 types in total. I just want to do a recap of kind of what we've done so far, so where we're at the moment, just very quickly. So remember, we've got this system of equations. We've got this system of equations up here. We've got one variable, we've got an equation of how one variable changes over time, and these are all our variables over here. So we've got how x changes over time, that's given by a linear equation, and y changes over time, that's given by another linear equation. Okay, and this is only true for the linear case, by the way. And we can combine these two equations into one equation using vector and matrix notation, which is what we've got here. And then because these coefficients will basically define these linear equations, is what separates, this linear equation from this linear equation from every other linear equation. It's the coefficients, right? Because the x's and y's is what every linear equation has got in common. It's just the coefficients which distinguish them. Then we can just consider this matrix of coefficients. All right, and then from that, we can kind of, if you like, boil down this matrix of coefficients into kind of what defines it, which is the eigenvalues. And then from those eigenvalues, of course, we can get the eigenvectors. Okay, so this is just a reminder of how we get the eigenvalues. Remember, we form this quadratic here, which is when I'm talking about p's and q's. This is where it comes from. I've just made a simplification for p. I think it's a plus d, and q is just the determinant of this matrix a, b, c, d over here. All right, and so we've talked about the case when the discriminant is greater than 0. So in other words, we've got real eigenvalues. Okay, and so when we've got real eigenvalues, we're looking at this general solution here. X of t is c1 e to the lambda 1t u1 plus c2 e to the lambda 2t u2, where u are eigenvectors and lambda are eigenvalues. Okay, and then we've got two different cases. Either the eigenvalues are the same sign, and in which case we're looking at this, which is something called a proper node, and we can have a stable case and an unstable case, or they're different signs, in which case we're going to have this, which is an unstable equilibrium point, and we've got a saddle going on. All right, then we looked at the case when the discriminant was less than 0, and that corresponded then to a square root which was negative, which of course meant that we would have to use imaginary numbers and complex numbers. So our eigenvalues would be complex, and when they're complex, we're going to be looking at this general type of solution. So x of t is e to the lambda t b cos beta t plus c sine beta t. Okay, and remember, because we've got a complex number, eigenvalues are alpha plus or minus beta I. Okay, so one would be the corresponding to plus, and the other one would correspond to the conjugate, so the minus. Okay, now the bit inside the brackets, the b cos beta t plus c sine beta t, just corresponds to a circle. Okay, so it's really the thing outside the brackets, the e to the alpha t, that's going to define what kind of growth term we have. And this is the real part. So basically we need to consider the different real cases. So either the real part is greater than 0, well, that's going to contribute to growth of this outside part, because it's going to make the outside part bigger, which means that we're going to have a circle which is going to be getting bigger over time. So if we're drawing a circle but we're kind of going outwards, yeah, and that's a spiral. So this is an unstable equilibrium point. And then if we consider the case when the real part is negative, then that corresponds by similar logic to decay, because we're getting smaller. So we're drawing a circle, but we're getting smaller each time, smaller as time goes on, so we're going to correspond to a spiraling inwards. That's a stable equilibrium point. And if alpha is equal to 0, we've just got e to the 0, which of course is just 1, so it's just going to correspond to a constant. Okay, so in other words, we're not going to move or deviate from this circle at all. Okay, and this corresponds to a circle. Now this is actually called a degenerate case, and this is what we're going to be talking about in this video. I was talking about 2 different types of degenerate cases in this video. So degenerate cases. Degenerate cases. Now, what does degenerate actually mean? Well, it's kind of got a couple of meanings in everyday world or everyday language, but the meaning that we're going to look at for this is it just means that it's lacking some quality. And the quality which we're looking at with equilibrium points and types of stability is literally whether they come into the equilibrium point or they go out of the equilibrium point. That is the quality that we're looking at when we're doing types of stability. Do they go into the trajectories, come in towards the equilibrium point, or do they go out of the equilibrium point? So do they diverge or converge, kind of thing? Well, that's the quality we're looking for. So if the degenerate case is it's lacking that quality, then it just means that it does neither. So it doesn't come in or it doesn't go out, it just kind of stays where it is. Okay, so in other words, all of these degenerate cases are always going to be structurally unstable. And like I say, when we're looking at this case, when alpha was equal to 0 and we got a constant, we're not deviating from the circle. So we're not coming in towards the equilibrium point, but we're not moving away from it either. So it's degenerate because that quality isn't satisfied. Okay, so this is an example of a degenerate case, but this is kind of, there's 2 different types of degenerate cases that we're going to look at in this video. So this is the first one, and it's called a star point. And basically, basically what this is about, so we've got degenerate cases is basically, if we've looked at before, we've looked at the case when the discriminant's less than 0 and when the discriminant's greater than 0. Then obviously the next case that we're going to be considering is when the discriminant is equal to 0. So maybe I should just consider that before we consider this point. So the discriminant, which of course is given by p squared, just to remind you, minus 4q, what's that equal to 0? Okay, well, if it's equal to 0, then basically, if you remember our quadratic that we got from the coefficient matrix, the eigenvalues of the coefficient matrix, minus p lambda plus q equals 0. Okay, when we plug this into the quadratic formula, so lambda equals minus p, effectively, so p minus p, sorry, plus or minus, well, this is now going to be 0, because this is our discriminant, okay, square root of 0, over 2 times a, so that's going to be over 2. So basically, our eigenvalues now are going to be p over 2, so they're going to be equal. Okay, and that kind of corresponds to what you know about discriminants. Okay, when it's greater than 0, you get 2 real roots. When it's less than 0, you get imaginary roots. But when it's equal to 0, you only get 1 root. So in other words, it's equal. The lambda 1 and lambda 2 are equal, and it's equal to p over 2. So this is the case when the eigenvalues are equal. Okay, so basically a star point. I want you to consider that we have our matrix, okay, our coefficient matrix, A, B, C, D. And what I want you to suppose is that we've got the case, this matrix comes out such that, it's a very specific case, but it comes out such that B and C are 0. Okay, so B and C are 0. So in other words, when we look back to our original linear equations, right up here, if B and C are 0, it basically means in this equation, so we've got dx by dt, we've got no y term. It may correspond to, depending on how you write it, if you write it the other way around, you either have no x. Basically, you get rid of a variable. So either you don't have a y or you don't have an x. And you'll have kind of the opposite case in the dy by dt, in the other variable with respect to time. Okay, so if you don't have in this case, I'm just considering b to be 0, so we only have an x in this term. In this case, I'm considering c to be 0, so we only have a y in this equation here. Okay, so that's basically the case which I'm considering. Okay, well, are you happy that when we form this, the eigenvalue matrix, the eigenvalue matrix, so A minus lambda I, then basically we can just read the eigenvalues off directly. Yeah, that A is going to be lambda and D is going to be lambda. So that D is going to be the other eigenvalue, and they're both going to be equal to P over 2. All right, let me just show you a little bit of justification by that. So let's take the determinant of A minus lambda I. So to take the determinant of A minus lambda I, so we've got A minus lambda, and then this is going to be 0. I've just said that B and C are 0. Okay, and then we've got D minus lambda. Okay, so I'm looking at this matrix now, A minus lambda, D minus lambda. Okay, and of course I'm setting that equal to 0. I'm taking determinants, so really I should draw straight brackets. When we put straight brackets around matrices, like modulus signs, it's not modulus, it's taking, if you like, the determinant. It's a bit like with vectors. When you put modulus around vectors, it means take the modulus here, take the square root and square it. Yeah. Here it's kind of the matrix equivalent, which is taking the determinant. Right. So let's take the determinant of this. So it's going to be A minus lambda times D minus lambda, and of course that's setting it equal to 0 because it's then minus 0, so that's fine. And then basically we can just read off that lambda 1 equals A and lambda 2 equals D. Well, I've considered the case when the discriminant is equal to 0 as well, so these two have to be the same. Okay, so therefore this has to be the same. Maybe if I just get rid of that and put that. So therefore they have to be the same, and they're equal to P over 2. And that kind of makes sense because, you know, we're sharing A and D, if you like. So it's, if you like, it's A plus D, that's what P is, over 2. So you're sharing A and D. So if you add the two together and divide those in half, then, you know, you're sharing it. So that's kind of what's going on here. So basically the main thing is, hopefully I've kind of justified that we've got this matrix now in this. I'm just considering it as a very, very specific case. I'm just saying, look, it may not be like this. In fact, the next case we're going to consider, it's not going to be like this. I'm just considering the very specific case where we can just read the eigenvalues off directly, where these two, the B and C, are 0, and we've just got A and D, and they're both equal to lambda, and they're the same. Okay, so basically the important part is that lambda 1 equals lambda 2. Well then, therefore, are you happy that when we form the eigenvectors from this, then u1 is going to also be equal to u2? So because the two eigenvalues are equal, we're going to have the same eigenvectors as well. So therefore, any eigenvector is a solution. Right? So let me try and draw what I've got here. So if I want to draw the general solution, or if I want to write out the general solution, remember when we had in the real case, let me just find it, it's here. We had the real case, we had a kind of a linear combination, I suppose, sort of, yeah. This is kind of a group of all the lambda 1s and eigenvector 1s, eigenvalue 1s and eigenvectors 1s and the constant 1s all put together in one group. And this is the eigenvector 2s and the eigenvalue 2s all put together, and constant 2s all put together in another group. Well, now we've only got one eigenvalue effectively because they're the same, and we've only got one eigenvector. So therefore, are you happy that I can just write it's just one constant e to the lambda t u? Yeah, I don't have to denote it by subscript. So this is kind of a very, very specific case, you know, when we've got this thing going on where we can just read the eigenvectors off directly. But we've got a very, very specific case. There's only one eigenvector. So let's kind of think about the fact that there's only one eigenvector, but actually any eigenvector we can choose can be a solution, right? Because if you like, it's lambda times xy, and that's the only condition it has to satisfy. So basically anything which is a multiple, any two values which you can put in here, which is a multiple of lambda, is a solution. Okay, so basically what does that look like? Well, look, I can draw this eigenvector in, yeah? I can draw this eigenvector in. I can draw this eigenvector in, you know, this is also a solution. I can draw this one in, that's also a solution. Yeah, I can keep going basically. Maybe if I draw that a little bit neater. I can keep going basically. And obviously it's really important, in fact, I think I didn't mention it before, but I know I mentioned it in the last video. Where the solutions, okay, these are effectively solutions. Trajectories are kind of the solutions. They're representing the solutions of our differential equations. Where they meet or where they cross, there has to be an equilibrium point there. That kind of makes sense if you think back to when, you know, you set up simultaneous equations, that when they're equal to each other, then when the two equations are equal to each other, that means they're sharing the same points. That's where they have to cross, right? Well, this is a very, very similar kind of idea. Where the trajectories meet, there kind of has to be a solution, an equilibrium point there at that point. So there has to be one in the middle. But at the moment, we don't know whether it's stable or unstable, except we do, because this is what's known as a degenerate case. Okay, so basically, if any eigenvalue is a solution, so all of these eigenvalues are solutions. This is u, this is u, this is u, this is u. Yeah, all of these eigenvalues are solutions, right? You get the idea. All of them are solutions. Therefore, we have to consider, well, lambda 1 and lambda 2, what are they equal to? They're equal to each other, but they're also equal to p over t. I showed you that earlier. Okay, so they're equal to p over 2. So in other words, the sign, you know, which direction we travel along these eigenvalues matters on the sign of p. So is it positive or is it negative? Well, let me put it to you this way. Let's consider the case when we've got p positive. Okay, so remember what p is. P is the leading diagonal, a plus d added together. Yeah, so we've got the coefficient matrix, just a plus d added together. It's what's known as the trace of the matrix. Don't need to know that. It's just a plus d. It's the leading diagonal added. Elements on the leading diagonal added together. So let's consider the case when p is greater than 0. So therefore, are you happy that as we go forwards in time, our solution, this is our solution if you want to consider it like this, okay? As we go forwards in time, we're just getting bigger and bigger and bigger because p is positive. Yeah? This increases as we go forwards in time because lambda is equal to p over 2. So if p is positive, therefore we've got a positive number here. Yeah? We've got a positive number here, which means that as we make t bigger and bigger as well, this whole term is just going to get bigger and bigger and bigger. So in other words, we're getting bigger and bigger and bigger, so we're moving away from the equilibrium point. Yeah? We're moving away from the equilibrium point. That's not away. Away from the equilibrium point. So we've got an unstable equilibrium point. Yeah, we're moving away from it. And this is kind of called a star point because can you see we can set up all these eigenvalues like this and they're all going to be going all the way around. There's infinitely many of them. But they're going to sort of radiate outwards like a star. Yeah? Well, that's the case when p is greater than 0. So we've got an unstable point. So if you like, it's a repel. Can you see that we're just being pushed away in all directions from the from the equilibrium point? We're at the equilibrium point. We've been pushed away in all directions. It's like an explosion. It's going outwards. Okay, so this is the case when it's repelled. So this is a repelling equilibrium point, or just unstable. That's absolutely fine. Okay. Now it's fairly obvious. Hopefully, you know, it's fairly obvious that if p is less than 0, then it's just going to be the other case. Okay, we're going to be sucked in. So we're going to have the attracting. We're going to be attracted. Okay. So we're going to have stable. But we can use the same kind of logic. So if p is less than 0, then therefore lambda is also going to be less than 0. because lambda is equal to p over 2. So our eigenvalue is, or eigenvalues, because they're equal to each other, is also going to be negative as well. So if you look back at our general solution, if this lambda is negative, what we're basically going to have is, as we make t bigger and bigger, if it's negative, we're effectively going to have, we'll effectively 1 over e to the lambda t, because this is raised to a negative power. So just by indices laws, x to the power of negative 1 is just equal to 1 over x, right? Just raise it to negative power, just flip it, yeah? So because lambda is now negative, we basically end up with this situation. As now we make t bigger and bigger and bigger and bigger, are you happy that this whole thing is going to get smaller and smaller and smaller? So in other words, our solution is going to get smaller as we make t bigger, yeah? So if our solution is going to get bigger as we make t smaller, then we're just going to have the same thing. We're going to have our eigenvectors kind of coming out in all directions. Okay, so here are eigenvectors. They can look anywhere they like. I'm just drawing these. Yeah, I'll talk about that in a minute. But because now we're less than 0, we're being basically drawn in. We're being sucked in. Our solutions are getting smaller and smaller and smaller. So if they're getting smaller and smaller and smaller, they're basically heading towards the equilibrium point, which, remember, we can move to be at 0, 0. So we just assume that our equilibrium point is at 0, 0. So we're being sucked in. Yeah, and this is what's known as an attracted equilibrium point, or just a stable equilibrium point. That's absolutely fine. So this is the case when p is greater than 0, yeah, and when p is less than 0, we're basically like an explosion. We're pushed outwards. I should note that I'm drawing little sort of arrows on the end of my eigenvectors. That's just to denote that the eigenvectors can go. That's just to denote that the eigenvectors can go in either direction. So it can go either positive or negative, because remember, an eigenvector is just a stripped down version of a vector. Yeah, it can be positive or it can be negative. All we're interested in is how they interact with each other, not necessarily interested in kind of where they lie in the plane, just interested in how they interact with each other. So yeah, these caps on the end just are different, so it doesn't matter too much here, but here it doesn't mean this eigenvector, the direction of this eigenvector goes out that way. It just means that we can take any value, so we can keep going in that direction. This eigenvector keeps going in that direction. But yeah, the actual path which we have to move along these eigenvectors is downwards. It's denoted by these arrows here. That's just a small little point, but I think it's good to make it. So they all tend to x the equilibrium point in this case. Okay, so that's a star point. So that's the first type of degenerate case. Then I'm going to consider the second type of degenerate case, and this is where our improper node comes in. So remember, when a proper node was when we were real, and the eigenvalues were at the same sign. Now we're considering the case again. It's still the same conditions. Let me just find it. The discriminant is still equal to 0, and they're still equal. Okay, but with the star point, we consider this very, very specific case. Okay, so this very, very specific case gave us the star point. So basically, in other words, we could just read the eigenvalues off directly. We had this kind of matrix set up, yeah, and they were both equal, yeah. Now, basically, we're going to look at the case where it's not like that. So the matrix is not looking like that. Okay, so we've still got the same case. Maybe I'll just write this down. So we've still got lambda, and they're still equal. Lambda is still equal. So what do I mean by that? Equal. And they're still equal to p over 2, right? P over 2. They're still equal to p over 2. We've still got the same thing. The discriminant is still equal to 0. So we've still got p squared minus 4q, whatever, is equal to 0. Okay, but now we've still got, now if we look at the coefficient matrix, A, B, C, D, yeah, it's the case when it wasn't before. We consider the case where basically we just had B and C 0. Now we consider the case where it's not looking like this. So we can't just read the eigenvalues off directly. So it's kind of, the generalised case of the case before. The case before was when we could just read the eigenvalues off. This is the case where we can't just read the eigenvalues off. But it's still going to be equal roots. Okay, and this covers it all. So we still have lambda 1 equals 2. Lambda 1 equals lambda 2. Okay, but now this comes from, so if I just take the determinant of this matrix now, the determinant of this matrix, we've got now A, B, C, and D. So in other words, B and C aren't equal to 0. So the determinant of A minus lambda I, okay, is going to be equal to A minus lambda B, the determinant of A minus lambda B, C, D minus lambda. Okay, and then obviously if we take the determinant of that and we set it equal to 0. So to take the determinant of that and set it equal to 0, we've got A minus lambda. Yeah, so that times that, D minus lambda. But now we've got this BC term that comes in, whereas before it was just 0. We've now got this BC term that kind of comes in on the end. And kind of this BC term kind of it dictates what happens to our eigenvalues, if you like. Sorry, our eigenvectors, if you like. Because we've said that lambda 1 equals lambda 2, so we've got a very special case where lambda 1 is equal to lambda 2. So basically, when we sort this out, we're still going to have lambda 1 is equal to lambda 2. All right? And so they're still going to lie in the same plane because of that. But because we've got this kind of extra BC term hanging on the end, we can't just say that it's equal to D and it's equal to, a P over 2. Well, it is equal to P over 2, but it's kind of a very special case. Maybe I'm not explaining that in the best way. But basically, because of this BC term before, which we didn't have before, this BC term now, which we didn't have before, basically we've got to say that when we form the eigenvectors, okay, so we form the eigenvectors, u1 is no longer exactly equal to u2. We're basically going to have one eigenvector, which is going to be longer than the other one. Okay, so one eigenvector is going to be longer than the other one. Okay, and that's just purely because there's a BC term hanging around on the end, which wasn't there before. When it wasn't there before, we just said that lambda u1 was equal to u2. But because of now this BC term that hangs around at the end, we're going to have basically, it's going to form a linear combination. Okay, and so therefore basically one vector is just going to be a multiple of the other. So one vector is going to be longer than the other always. Yeah, so now we need to consider whether the eigenvalues are positive or negative. Okay, because they're going to be equal to P over 2. They're going to be equal to P over 2 still. But now we need to consider, is this positive or negative? So in other words, we need to consider what happens to P, similar to before. So what happens if the eigenvalues are greater than 0? Okay, so the eigenvalues are equal to this. It's similar to considering P, like we did before. But now I'm just going to write it as lambda, just because I can. Okay, so we've still got our general solution. So we've still got x of t. Okay, our lambdas are going to be the same, but because our eigenvectors are going to be slightly different. They're just going to differ by a multiple of each other. So we've now gone back to this kind of original, form, but we've still got the same eigenvalues in both, kind of thing. Let me write it down and see if you can make sense of this. So this is u1, all right. Yeah, maybe I'm going to write, hang on, wait a minute, let me just get this right. Yeah, so just to get it right, because I've used this up before, basically it's exactly the same idea. I'm just going to write ku2 instead of u1 there, and I'm just going to have plus c2 e to the lambda t, and then this is just going to be u2. Yeah, that's better. So basically just one, these are two, they're basically the same eigenvector, okay, but just one's a multiple of the other. So I think that's the right notation with what I've got up there. It's consistent with what I've got up there. Okay, so if it's greater than 0, we've got this thing going on, and actually we've got this thing going on in both cases. So whether lambda is positive or negative, this is still the general solution now. So this is basically the general solution that we're going to be considering. All right. Now, if lambda is positive, okay, which one is going to be the bigger matrix? Which one is going to be the kind of the bigger one, the more dominant term? Well, can you see it's obviously going to be this one, because we've got k times u2. These are basically identical terms because we've got the same lambda in both. And the same u2 in both. It's just this one's got a multiplier term in it. So this one's obviously going to be bigger, okay, if lambda is positive, right? So basically as we go forwards in time, as t goes to infinity, if you like, we're pulled towards this eigenvector. If you want kind of a visualization of what's going on here with this u1 and ku2, think of twins. Okay, we've got a set of twins. Got a set of twins, this one, okay, and this one. Okay, so one is really big. They're exactly the same kind of in genetic makeup kind of thing. They're very, very similar in genetic makeup. So identical in genetic makeup. Identical twins, let's say. Except one is taller than the other. So this one's short and this one's tall. This is the same kind of thing. We've got the same genetic makeup of eigenvectors. It's just one is longer than the other. Okay, so basically as lambda's positive, we're going to get pulled to the one with the multiplier term. In other words, we're going to get pulled to the taller one, the longer one. So we're going to get pulled to this guy over here, the tall guy, yeah, if lambda's positive. So basically what have we got? We've got our eigenvector solution. So, yeah, this is our eigenvector solution. So we're going to call it u2. Okay, eigenvector solution u2, and basically we're going to get pulled to the longer one. So in other words, we're going to get pulled to the bigger one. Well, the bigger one's obviously going to be at the extremities. Yep. So we're going to get pulled to the bigger one. So in other words, we're going to get pulled that way. Yeah, and likewise we're going to get pulled that way. Yeah, so we're going to basically be pulled out, if you like. We're going to always be pulled to the longer one. Hopefully I've made that clear. Okay, so basically we're being pulled away from the equilibrium point. So if lambda's greater than 0, we basically end up with an unstable equilibrium point. Now we consider the case when lambda's less than 0. Notice, this is the reason why I'm considering lambda instead of p. It's exactly the same as considering p, so p is greater than 0. That's exactly the same case. That was p is less than 0, but I'm just looking at what happens to lambda. Okay, so now if lambda's less than 0, let's look back at our general solution. Okay. If lambda's now less than 0, it basically means that this is a negative value. So as we make t bigger and bigger and bigger, this one is going to become the dominant one. Yeah? So we make t bigger and bigger and bigger, because this is kind of the smaller value. If lambda is now negative, if we make bigger and bigger and bigger, this one, we're going to be drawn to this one much more. Okay? And so, yeah, we basically end up with this point. So this is u2, this is u2, and we're basically going to be drawn in towards the shorter value. Yeah, the shorter twin, if you like. It's going to be pulled into the shorter eigenvector, and the shorter eigenvector is obviously going to be the one closer to the equilibrium point. So we're going to be pulled in this way. Okay, so hopefully that makes a bit of sense. Oops, didn't mean to do that. There we go. Hopefully that makes a bit of sense. Yes. Anyway, there we go. Okay, so those are the degenerate case. We've got the star point in the improper node. Now the last one that I'm going to be looking at is this thing called the equilibrium line. Now this very, very rarely comes up, okay, sort of, in general cases, but it does come up and it does exist, and so kind of for completeness, it makes sense to do it, okay. And basically what we need to consider now, I want to basically consider, so we've got lambda squared, what have we got, minus p lambda plus q equals 0. Okay, so we've got this same quadratic that comes out of the coefficient matrix. Okay, and I want to consider the case when q is equal to 0. So if q is equal to 0, and presuming that we can't have a 0 matrix, okay, because obviously we've got our linear system of equations, dx by dt and dy by dt right up here. Okay, if it was all equal to 0, then this right hand side was equal to 0, so then dx by dt is equal to dy by dt. 0, so we just don't bother considering that. It just doesn't exist. Where is it? I've done lots. There we go. So there's our coefficient matrix. It can't be equal to, or be 0. So in other words, I do have to have some real values in this matrix. Okay. Well, now if q is equal to 0, what are we left with this quadratic? We're just left with lambda squared minus p lambda equals 0. So in other words, this q term disappears. Remember, q is just a determinant of the matrix. So basically, this is another way of saying this is that the determinant of the matrix A is equal to 0. Okay, so if we haven't got, so let's just stick with this. We haven't got a q term, so therefore that goes away. So therefore, when we factor this out, we get lambda times, what's this? Yeah, lambda minus p, okay, equals 0. So that implies that we get lambda, so one eigenvector being 0, and one eigenvector being a positive number, being p, which of course is a plus d. Okay. Right, well, what's going on there? So basically we get two eigenvectors out. One of them is either positive or negative, depending on what A and D are. Okay, but the other one is always equal to 0. So what does that mean? Well, when we solve our eigenvector equation, so when we find the eigenvectors, remember we're solving this equation, where x is just now our eigenvector. Okay, really I should write u. Yeah. U, because that's the notation we've been using so far. So now we've just got u. So when I try and solve this, effectively what I'm asking is, well, we've got lambda here, which is going to be 0 times an eigenvector. So in other words, we've got 0, so some eigenvector xy. Okay. Well, can you see that there's an infinite number of solutions for these? We can literally choose any vector we like. It will always work. Okay, and particularly when you sort of form your eigenvector from this eigenvalue, so we get some eigenvalue from out of this. Let's call this lambda 2, let's call this lambda 1. Okay, so let's call this lambda 2. So we'll get an eigenvector, we'll just get a certain eigenvector out of this one. So this is lambda 2, u2. So we'll get a definite eigenvector out of this one. But because we've got 0 times this, it can literally be any eigenvector we like. Okay, so it can be this one, it can be this one, it can be this one, it can be this one. It's literally any eigenvector we like. There's literally an infinite solutions, or infinite many solutions for this eigenvector. Okay. If you want to think about it from the other point of view, if you want to go back to this thing, which is the determinant of A, well, what does the determinant of A equal to 0 mean? It means that it's singular. It means it's singular, which in kind of your and my language, it says no inverse. Okay, so remember right back at the beginning when I was forming linear systems of equations, we had dx by dt, okay, and I wanted to set that equal to 0. Okay, so I wanted to set, to find the equilibrium point. Okay, and of course dx by dt was equal to ax. So in other words, I'm saying that ax equals 0. Okay, so this is looking at the same thing, just kind of on the left-hand side now. Here, before I was looking at it from the right-hand side. Now I'm looking at the left-hand side. I'm setting the left-hand side equal to 0. Okay, so if this is now equal to 0, well, a doesn't have an inverse. Okay, if this is true, if it's singular, it doesn't have an inverse. So therefore, I can't find a specific solution. Okay, so I can't say it's equal to the 0 vector, okay, because I can't find A inverse. Right? Maybe you might want to go away and think about that. Okay, so basically what this means is that I can choose any vector I like. Okay, any vector I like will satisfy this equation. So in other words, I've got an infinite number of solutions that can kind of intersect my definite eigenvector, which comes from my lambda 2 equals p. Yeah? With me so far? So basically what I'm going to do is I'm going to assume that we're at the origin. I'm going to assume that we're origin. I'm going to go back to dx by dt and dy by dt, my linear system of equations. Remember, this is ax plus by, and this is cx plus dy. Okay, I'm going to assume that we're at the origin, that we can, if we find our equilibrium point, it's basically we're setting both of these equal to 0. Setting both these equal to 0 to find our equilibrium point. Okay, and I'm going to assume that we're basically at the origin, which is why I haven't got any constant terms on here. Okay, because remember, we can shift it to be at the origin by using x tilde. Okay, shifting the whole function by every point in our function by our equilibrium vector, our equilibrium points. Okay, so basically now if I just rearrange this, so basically I'm saying that I can set these two things equal to each other. Ax plus by equals cx plus dy. So I'm just showing you kind of the basics behind it. So you've got ax plus by equals cx plus dy. So I'm finding the equilibrium points by setting these two things equal to 0. So therefore I can set these two things equal to each other because I'm setting them equal to 0. Okay, I'll do a bit of rearranging. So I'm going to move all the y's on this side. So I'm going to by minus dy is equal to cx, all the x on this side, minus ax, do a bit of factoring. I end up with b minus d times y equals c minus a times x. Yeah, and then I can just get y in terms of x. So y is equal to c minus a over b minus d times x. So this is, as you can see, an equation of a straight line. It's y equals mx plus c. Okay, where c is just 0. So my gradient is given by c minus a over b minus d. All right. So in other words, I've got a straight line. I end up with a straight line. Yeah, and this kind of corresponds to my definite eigenvector. Yeah, so I've got my straight line here. Okay, I'm actually going to draw two of them out. So I'm going to consider two different cases, slightly different cases. So what I basically need to do is, if you consider that P is going to be equal to A plus D. Okay, I'm just considering this vector equation of a straight line, but I'm just looking at it now from another point of view. So I'm trying to kind of, if you can't really see this, and if you want to kind of show the algebraic point of view, I'm basically deriving the equation of a straight line. So as you can see, this eigenvector would clearly depend on A plus D. So I need to basically consider different values of P. Okay, well, maybe if I look at it from this point of view, if P is positive, can you see that if P is positive, lambda 2 is going to be positive, so therefore all eigenvectors are going to basically be moving away, okay, from this eigenvector. Okay, and if P is negative, they're going to basically be moving towards. Let me try and show you this, using this example. So if P is positive, P is greater than 0, I'm going to basically end up with negative here. I'm going to end up with a negative gradient. Okay, so in other words, I'm going to be moving away. I'm being pulled away from this line. Yeah, in both directions. And if P is negative, P is less than 0, I'm going to basically end up with a positive number here. Okay, so in other words, I'm being pulled down by this, I think. Yep. There we go. Okay, so like I say, this is kind of like an extra, so I'm being pulled towards this, being pulled away. If you want, this is a repel, and this is an attractor. Okay, so hopefully that makes a bit of sense. So basically what we've done is we've done degenerate cases. We've got a star point, okay, and that's a very special case where we've got this kind of matrix set up where we can just read the eigenvectors off directly, okay, and either it's like an explosion, we're being pushed outwards, and that's the case when our eigenvalue is greater than 0. If our eigenvalue is less than 0, we're being pulled inwards, being sucked in all directions, like a black hole. And in proper node is when they're still equal, but we haven't got this case where we can't read the eigenvalues off directly. Okay, so we have to kind of consider one eigenvector as a multiple of the other, so one is taller than the other one. And then we kind of get this case going on, kind of almost like being swished in or out. And then finally the equilibrium line, which is just where we've got a singular matrix going on. Okay, and we just end up with this equilibrium line. So so now instead of just having one single equilibrium solution, I should say this, instead of having one equilibrium solution, now we've got an infinite number of equilibrium solutions. Because if you like, this is our eigenvector being equal to 0. Okay, all down here. Okay, we've got an infinite number of them. Okay, now remember where our solutions cross, that corresponds to an equilibrium point. Well, therefore, if we've got an infinite number of eigenvectors, we can put them literally anywhere, okay, then we must have an infinite number of solutions. Well, the infinite number of solutions where it crosses this kind of definite straight line, this is like U2, is where it crosses this eigenvector. Well, if it crosses an infinite number of places, then basically everywhere along this eigenvector is a solution. So in other words, now instead of having a single point like that, we've basically now got an infinite number of single points. In other words, the whole line is a solution. Okay, like I say, don't worry if you don't get that last one too much. As long as you kind of understand the basics of it, it very, very rarely comes up, but it does exist. So just kind of complete this. That's why I've done it.